Today we will understand the energy possessed by a particle who is performing SHM. Now particle which is performing SHM has velocity, so it has kinetic energy, as well as it has a force which is trying to bring the particle back towards the mean position. So it is having restoring force, and due to restoring force it is having a kind of potential energy. Kinetic energy is simple to calculate. It is half mv square. Now we consider the particle at a position when it is x distance away from the mean position. At this point its force is m into a, where a is omega square x, and we can easily observe that force and acceleration both depend upon the displacement. That means at every point of the motion, both force and acceleration are changing along with the velocity, with the displacement. So kinetic energy can be written as half mv square, that is half m, and v, we have already calculated v, that is omega square under root a square minus displacement x square, where a is amplitude and square of this value is velocity of the particle at displacement x. So simplify it, half m omega to the power, just correct it beta, it is omega only, it's not square here. So omega to the power 2 and a square minus x square. Now this is kinetic energy, and potential energy can be written as work done by restoring force to bring this particle back towards the mean position. So how we calculate work done? Let the particle be at distance x from the mean position when we are observing it, and now at this moment force is ma, that is m omega square x, and now we take the displacement of the particle to be dx, very small displacement, so that during this displacement this restoring force can be taken to be constant. So work done by the restoring force when it is displaced by the distance dx, it can be written as, potential energy can be written as work done by the restoring force while work done by the conservative force is negative if we are considering change in potential energy. So change in potential energy is equal to minus work done by restoring force, and work done by restoring force can be written as F dot dx. This is small work done in the displacement dx. So work done during the whole process can be written as integral 0 to x. Now what is x? X is displacement of the particle from the mean position, and we are considering change in potential energy when particle is at position x minus when particle was at its mean position. Now at the mean position the force is 0, therefore the potential energy will also be 0, and potential energy at position x can be written as simply F dot dx. Substitute the value of F, that is m omega square x and dx. Now consider the displacement to be right side and the force in that case will be towards left, the F dot dx will be F dx cos 180. So here cos 180. Now this 180 minus 1 from cos 180 will neutralize this minus sign. So we can write integral 0 to x m omega square x dx is potential energy of the particle performing SHM at any position x from the mean position. Now solve it. M omega square can be taken out of integration, so 0 to x dx, and this can be written as m omega square x square by 2, and we have to substitute the value 0, the lower limit, and upper limit as any general position x. So this is written as m omega square x square by 2. So now check out, we are having kinetic energy as half m omega square a square minus x square, where x is the position of the particle from the mean position, displacement of the particle, and we are having potential energy as m omega square x square by 2, where again x is position of the particle from the mean position. So total energy of the particle will be addition of kinetic energy and potential energy. So let us calculate the total energy of the particle, and it is kinetic energy plus potential energy, and that is half m omega square a square minus x square plus half m omega square x square. Now half m omega square x square will get cancelled, and we will be left with total energy equal to half m omega square a square, and this value remains constant throughout the motion, although kinetic energy keeps on changing into potential energy during the motion, and potential energy keeps on converting into kinetic energy during the motion. At the mean position, where x is 0, kinetic energy is maximum, that is half m omega square a square, because velocity is maximum at mean position, while at x equal to 0 you can see that potential energy is 0. So potential energy is 0 at mean position, while kinetic energy is maximum, and that is half m omega square a square at mean position. At extreme position, potential energy is maximum, half m omega square a square, while at extreme position, when you substitute the value of x as amplitude a, this expression will become 0, and kinetic energy at the extreme position will become 0. So total energy in the SHM, simple harmonic motion, remains constant, although the two energies keeps on interchanging from one form to other form. Now we can draw the variation of kinetic energy and potential energy along with the displacement from the mean position. Now just look at the expression. Kinetic energy is equal to half m omega square a square minus x square, while potential energy is half m omega square x square. So kinetic energy is maximum at mean position, and minimum at extreme position. So if this is the mean position, then kinetic energy is maximum at mean position. So kinetic energy is maximum at mean position, and the value of maximum kinetic energy is half m omega square a square, which is the total energy of the particle also. But at extreme position, that is, if you take this as minus a, this as origin, and this point as plus a, the amplitudes of the two sides, then kinetic energy will follow the variation according to the graph like this. While potential energy is minimum at origin and maximum at extremes equal to half m omega square a square. So potential energy can be plotted as the graph of this shape. So variation of kinetic energy and potential energy, and along with it at any point, the sum of kinetic energy plus potential energy. Sum of kinetic energy plus potential energy is equal to the total energy, that is half m omega square a square. So if you add this value and the potential energy equal to this value, then the sum will become half m omega square a square. This value here will be added at this point. So total energy at every point of the motion will remain constant, and there is a point where kinetic energy and potential energy are equal to each other. So that point can be calculated just equating the value of kinetic energy and potential energy. Let this point be x from the mean position. Then kinetic energy at this position will be half m omega square a square minus x square, while potential energy will be half m omega square x square. So taking half m omega square x square on this side, we can write half m omega square a square is equal to half m omega square x square plus half m omega square x square. Now cancelling the terms m and omega square and half, we can find a square is equal to 2x square, or x is equal to plus minus a by root 2. So this is the position. X is equal to plus minus a by root 2, where kinetic energy is exactly equal to potential energy. So this point where the two curves are intersecting, this is a by root 2 at this side and minus a by root 2 at this side. So this is all about the energy possessed by a particle performing simple harmonic motion.